In this chapter, we're going to talk about sound wave. Actually, this is not the first time I talk about sound wave, right? Because in the previous chapter, we actually talk about some properties of the sound wave already. That is the resonance and standing wave created by sound wave in open and closed tubes, right? Uh, but then we're going to talk about common properties of the sound wave in this chapter, like speed of sound, sound intensity, and uh, sound level. Okay, as you know, that sound wave act as a longitudinal wave in air, and I would say that it also acts as a longitudinal wave in most of fluid. Um, and the speed of sound can be uh, expressed as this equation. It depends on the bulk modulus and the density of the medium. Um, well, what is really bulk modulus? You might not learned this yet. So let's talk about the bulk modulus. Bulk modulus can be expressed as this equation. When you have an object of volume V, and for example, you or act you apply force in all the direction to this object, like you put this in water deep down to the bottom of a container. Well, this object will feel the pressure by water at that depth, and uh, the volume of the object depends on how elastic the object is. Uh, well, the volume supposed to be changed, right? And in this case, should change in the direction that it's become smaller or less volume. And delta V in this equation defined as the final volume minus initial volume, right? And you see that delta V is negative value. And in this case, when the volume is let's say smaller, the pressure should be larger, right? This should be in the opposite direction. That's why this bulk modulus, this equation for bulk modulus has this negative sign. So if delta V become negative, this delta P should be positive, and bulk modulus always become positive. And think about the other way around. So if you apply force to let's say expand this object, the volume become delta V become positive and pressure become negative. So that's the other way around. And in that case, you also get the bulk modulus positive, right? Okay. And this is bulk modulus. Okay. And the other factor is density, right? Density, you know what it is. It's how dense the medium could have. At higher temperature, when you compare, for example, in air, you see that the speed of sound is larger in this table. It's larger at higher temperature, and you can probably express this using this simple equation. Vt is the speed of sound at temperature T equal to 331 plus 0.6 times T. T is the temperature in degrees Celsius. And you see that when temperature go higher, speed of sound also higher. That because the density become less, right? And you can actually see that makes sense from this equation. Okay, and that's the one. Before we move to the next slide, I would say that sound wave doesn't need to be longitudinal wave always. Sound wave can act as a transverse wave when it travels in, for example, solid, or can act as both longitudinal wave and transverse wave. But I will not go into details of this. All right. Okay. Next thing about sound waves. Uh, well, uh, you know that sound wave is also like some other mechanical waves. It requires medium to travel, and the medium that the wave travel through uh, going to oscillate in simple harmonic motion. So the sound wave can be also defined as a sine or cosine function, just like the case you have seen before, like wave on the string. But a special thing for the sound wave is that you can write the wave function in the form of displacement, or let's say displacement function, or change in the pressure or pressure change function. And these two always are, I will not call it out of phase, but you know the phase difference is always 90 degree, or one is cosine and the other should be sine. So, or I would say that when the displacement of the particle is maximum, so it's farthest from the equilibrium position in simple harmonic motion, the change in pressure is zero. You see, you can have a look at the graph here. But anyway, I'm not going to really talk about this in much details. I will just go on. Just want to show you this is, you know, sound wave is just like some other type of wave and can be defined as the equation. And in this case, for the one-dimensional traveling sound wave, you can write also similar functions as you have seen before for the wave on the string. Okay, you can look at the the derivation to get the sound wave function, but I will not really focus on this, and of course you will not see anything like this in the exam. Okay, so we move on. So next we're going to talk about the intensity and sound level. Intensity, of course, it depends on the source power. I mean, you think about, you have a speaker, and when you increase the volume of the speaker, you get higher. I mean, you have to apply more power into the speaker, right? And the sound that produce become more power, and that when we talk about the power of the source, right? This big P. And the intensity is defined as this big P divided by the area, because sound wave is a spherical wave. So it's when you have a point source like speaker that count as a point source, sound wave just, you know, spread in all direction as a sphere. So the area of the sphere surface is act as a area that the sound wave spread on. So the intensity at position R can be defined as P divided by 4 pi r square. That's actually this equation. Okay. Well, similar in the case of ripple wave, but the ripple wave, like I mentioned, is a circular wave, right? The area is become the circular line that the ripple wave spread through. And that in this case is different. You know, this for the ripple wave, the power, I mean the intensity is the power divided by 2 pi r. Okay, but okay, we're gonna focus on this equation for the sound wave. Next, I would like you to know, this is just, you know, just to inform you that this intensity is dependent on the amplitude of the sound wave square. What is the amplitude of the sound wave? You can find this amplitude from the displacement function. Here is Sm here. Okay. But just to let you know, this is something that I have to tell you, but we might not be go into details how it's come from. But okay. But yeah, please know this. Let's say okay. Next thing are the sound level. This is very important. Even though I just put this on the slide with some other information, but this slide is very important. Let's say. So first of all, you have to know that the intensity is the power of the source divided by the area. And next thing, you have to know that what is really the sound level relative to the sound intensity. This is the sound intensity, right? Sound level equal to 10 decibel. This has a unit of decibel, all right? 10 decibel multiplied by log intensity divided by I0. What is really I0? We call standard reference intensity. Okay, this, for example, if you have 10 to minus 5, if you take log of this 10 to minus 5, you get minus 5, right? But if you get log of 10 to 5, you get 5. So you can imagine, if you want to compare the intensity of 10 to minus 5 and 10 to 5, this is going to be like 10 order of magnitude to, I mean, it's really, very large difference. But when you compare minus 5 and 5, it's just, well, very close number in the same rank. That's why we use log for the sound level. I mean, that's why sound level must be defined, because the sound level at different distance can be really much difference. That what I mean to say. Okay, and this is how show you how to relate the intensity with the amplitude square. I mean, what we talk about in this slide when we talk about the wave function. Okay, but like I mentioned at the beginning, that we're not going to talk about it in much detail, but yeah, when I ask you what is the relationship between the intensity and the amplitude of the wave, you should know that I is proportional to Sm square or amplitude square. That's what I want you to know. Okay. Okay, we talk about the sound intensity and sound level a bit more. As you know that sound intensity, okay, I'm not going to repeat, it's just in the what's called inverse square law. For example, from the source, if 2 meters from the source, you get 1/4 of the power that produced by the source, right? At 3 meters, you get 1/9. And you imagine that you want to compare sound intensity at very close distance from the source to a very far distance, like 100 meters, and compare with the intensity at 1 meter, for example. This will be really, really large difference, and this is not suitable to compare, like I mentioned before. And that is the reason why we need this sound level. It's quite easy to compare, because the value always in the same rank. All right. Okay. Let's try with some exercise together. So the first one is very simple one. The source of a sound wave has a power of uh, 1 milliwatt, right? And the distance 3 meter away, what is the intensity at that position, and what is the sound level in decibels at that position. Okay. So it's quite simple. So this is I. Let's say that this is I at 3 meter equal to P. P is 10 to 1 10 to minus 3 divided by 4 pi r square, and r is 3, right? And that actually is very simple. And in this case, you should get if 8.84 10 to minus 6 watt per meter square. Then sound level, you know that sound level in decibel I will call it beta, and probably beta also at 3 meter equal to 10 decibel multiplied by log I, that is 8.84 10 to minus 4 divided by 10 to minus 12, and you should get the answer actually in the unit of decibel, that is now 69.5, about 69.5 decibel. Okay. Go to the next exercise 2. Gonna be the last that we try in this part. What is the difference of the sound intensity, sound level change, and the distance of 5 meter and 100 meter from the sound source? Okay, in this case, the sound source produces at the power of 10 watt. Right. So now we're gonna compare, right? The first example, you just calculate one single value for each, and this we're going to compare. You know that I is P over 4 pi r square. If we define R1 equal to 5 meter and R2 equal to 100 meter, so we can really say that I1 divided by I2 equal to R2 square divided by R1 square, right? And in this case, you can compare the ratio, right? And that is 100 square. That know that this is like 10,000, and this is 5 square. You get 25. This is quite a big difference. That's 400 times, right? Yes, 400 times. But when you compare the sound level, you do it in a similar way, but in this case, I would say that the ratio might not be effective. I mean, it's usually when you compare the difference in sound level, you might get this, let's say, like delta beta. So let's say is a beta 1 minus beta 2. Okay, and in this case, you can either get 10 log or I1 divided by I2, right? Okay, let me recall you that the sound level in decibel can be expressed as 10 log I divided by 10 to minus 12, or this is we call I0. Okay, and because the subtraction of log can be expressed as the ratio, right? So in this case, you're gonna get beta 1 minus beta 2 equal to 10 log I1 divided by I2, and this can make it okay. I1 is you know the ratio, right? Okay, you know the ratio. This is 400, right? So this is like, okay, 10 multiplied by log 400, right? And the answer actually is 26 26.202 decibel, right? You see that this is like what? Oh no, this is ratio though, no unit. Okay, this is like 400 times. If you compare, so let's say the intensity at 5 meter getting intensity of 400 times compared to at 100 meter, but when you compare the sound level, the difference is 26 decibel approximately. Okay.